notes 6.6 are on solving logarithmic equations. And before we go ahead and actually solve these logarithmic equations, I just want to remind you guys about the domain of a logarithmic function. So if I were to take a look at Desmos and take a look at what it looks like if I were to graph out a logarithmic function right here. So I'm going to go to functions and I'm going to type in log right here. This is log base 10. You can do any log you want. If you remember, our domain is restricted to all values greater than 0, okay? And it does not matter what our base is right here. So if I were to use a different base right here and I did log base 2 of x instead, it still has a domain that's restricted where x is greater than 0. And the reason why this happens is because we can't have an answer that is if I raise 2 to any exponent, my answer will always be bigger than 0. Just like when we did the inverse right here, the domain here was it was all x values, or sorry, the range here was all at y values greater than 0. We're swapping them now. The x and the y are now interchanged. So this right here is telling us that our x values can't be bigger than, or have to be bigger than 0. Okay. Now, what if my input here was 2x minus 5 instead, for example? That shifts my domain over where x has to be bigger than 2.5. So if you look right here, it has to be bigger than 2.5 because we set what's in our brackets here equal to 0 right here. Okay, so just a reminder, I want you guys to write yourselves a really important reminder here, please. Sorry, that was my dishwasher, just ignore it. So a really important reminder is if we have y equals log base b of any expression right here, a has to be bigger than 0, always. Okay, so let's apply this to question number 1. So number 1 says solve the following equations. So in A, it says log base 7 of 3x minus 5 is equal to log base 7 of 16. So the first thing I need to do is I need to say that this 3x minus 5 has to be bigger than 0 so I can know what my restrictions are, because knowing my restrictions is going to be really important when we're trying to look for extraneous solutions. So 3x is greater than 5, which means that x is greater than 5/3. So these right here, my restriction is x has to be greater than 5/3. Okay, so let's go ahead and solve this right here. I have log base 7 of 3x minus 5, and then I have log base 7 of 16. Since they're both log base 7s of an expression right here, then I can just simply set these two pieces equal to each other. So I can just say 3x minus 5 equals 16, and then I can just solve it like I normally would. So add the 5 to both sides, you get 3x equals 21, so x equals 7. 7 is bigger than 5/3, so it's not an extraneous solution, so this is my answer here. Okay? All right, so now let's take a look at the next one. The next one's not a logarithmic equation. We're going to mix and match some logarithmic equations with some exponential equations. So if you take a look right here, in order for me to be able to solve this, I want to get this 3 alone, this base alone. So I'm going to divide both sides by 2. So I get 3 to the power of x minus 4 is equal to 25 over 2. Okay, so now what I can do is to get this exponent out of here, I'm allowed to log both sides. So I'm going to log both sides. And this exponent, remember, goes out in front. So I end up getting x minus 4 times the log of 3 is equal to the log of, and I'm just going to rewrite this as 12.5 because that's not going to end up being a repeating decimal. So it's not a big deal for me to use that to solve. Okay, so now I need to distribute the log 3 through to everybody right here. So I get x log 3 minus 4 log 3 is equal to log of 12.5. Okay, I'm going to add this 4 log 3 to this side so I can isolate this x. So x log 3 is equal to log of 12.5 plus 4 log of 3. Okay, now to get this x alone, I can just divide both sides by log of 3. So x is equal to log of 12.5 plus 4 log of 3 all over log of 3. And I can type that into my calculator and get an approximate answer. Now, the nice thing about this type of a question is that there are many ways that you can solve it and many different formats for the way your answer might look, but you still could get the correct answer. There are lots of methods that you could follow in order to solve it. So if you can think of another method for this, that'd be amazing. Show me, and I'd be very impressed with you. And if you can, that means that you really understand what's happening here. Okay? So here I'm going to go to my functions, and I'm going to type in log of 12.5. Okay? And then I'm going to close my bracket, and then I'm going to type in plus 4 times, I'm going to do log again of 3. Sorry about that. Let me just fix this really quickly. Plus 4 times log of 3. And then I'm going to close my bracket here, and I'm going to divide that by log of 3 right here. And I get my answer is about 6.3. So here, my answer is approximately 6.3. Now, I want to use the Desmos graph in order to double check my answer to make sure that this is right. So what I'm going to type in right here, for my first graph, I'm going to type in y equals 2 times 3 to the power of times 3 to the power of, and then I'm going to open up my brackets because Desmos doesn't like exponents that are more than just one term. Okay, so that's that graph right there. And then I'm also going to graph out y equals 25. And I'm going to see what happens up here when I scroll up to 25. I'm going to see where they intersect with each other. And they intersect at approximately 6.3, so that answer here is correct. Okay? All right, so for the next one that we have here, this one's a little bit trickier. We have to use our log rules, or our laws of logarithms in order to be able to solve this. But before we do that, the first thing I want to do is identify any restrictions. So I'm going to look at all my variables here. So I've got log of 30x, log of 5, and log of 12. This is the only one with a variable. So 30x has to be bigger than 0, which means our final answer has to be bigger than 0. This is my restriction. Now, if you remember, if we have subtraction with the same base, we're allowed to go ahead and divide these values right here. So I can say that this left side right here is equivalent to log base 2 of 30x divided by 5, and then I'm just going to copy down the right side right here. Okay, so then here I can say that log base 2, I can simplify this to 6x is equal to log base 2 of 12. Okay, so here when I go ahead and I solve this problem right here, I can see since it's log base 2 of one expression is equal to log base 2 of another expression, I can set those two equal to each other. So 6x equals 12, which means x equals 2. 2 is bigger than 0, so it satisfies my restrictions here that as long as x is greater than 0, it will work. Okay. All right, awesome. So let's take a look at D right here. So D is a little bit trickier. Same thing, we're going to write our restrictions right here. So x has to be greater than 0. Okay, that's the first one. And x squared has to be greater than 0. But when I solve for x here, it's saying pretty much the same thing. So those are our restrictions that we have here. Okay. Now, a reminder that if we have addition, it means to multiply as long as we have the same base. And our base here is an invisible 10. Okay, so we can say log of x times x squared is equal to 12. So I'm going to simplify this here into log of x to the power of 3 is equal to 12. Okay, now just a reminder that if we have a to the power of log base a of x, that's just going to equal x right here. So to get the log out of here, so I have the x alone, I can raise each side to the base that we have here, and our base is an invisible 10. So if I raise this and I write this as 10 to the power of log base 10 of x to the power of 3 and 10 to the power of 12, this right here, this whole piece right here, just turns into x to the power of 3 is equal to 10 to the power of 12. Okay, now my x is out of there, so I can actually solve for x. In order to be able to solve for x, I have to take the cube root of this answer right here. So notice how all of your knowledge of logarithms and exponents and the laws of both types of both things are necessary in order to be able to solve these questions here. So I've got 10 to the power of 12, but that's being raised to the power of 1/3 because the cube root means the power of 1/3. And if you remember, when we have a power to a power, we can just multiply. So 12 times 1/3 is 4. So x is equal to 10 to the power of 4, which is essentially just 10,000. So my answer to this is x equals 10,000. Okay? All right, so in question E, we want to solve 2 log base 4 of x minus log base 4 of 4x plus 3 is equal to -1. So I'm going to identify what my restrictions are first. So x has to be greater than 0, and then 4x plus 3 has to be greater than 0. So right here, when I isolate the x, I get 4x is greater than -3, which means x is greater than -3/4. But this right here encompasses everything that's here and more. So this one right here is the more specific restriction because x can't be bigger than -3/4 and bigger than 0. So I'm going to go with the higher one, so x has to be bigger than 0. So when I go ahead and solve this right here, I have some subtraction in this problem. So because I have subtraction, I need to write this log base 4 as a division problem right here. I also have this coefficient here, so that means I can bring this out in front right here. So I'm going to do this in 2 separate steps. So I'm going to say log base 4 of x squared minus log base 4 of 4x plus 3 equals -1. So then I'm going to put this all together, and I'm going to say log base 4 of x squared over 4x plus 3 is equal to -1. So now, in order to be able to solve this, I'm going to raise both of these sides with a base of 4. So 4 to the power of log base 4 of x squared over 4x plus 3. And I chose 4 because the base is 4 in both of these. And I know that 4 to the power of log base 4 of anything will cancel all of this stuff out. And I end up just getting x squared over 4x plus 3 is equal to 4 to the power of -1. Well, I know 4 to the power of -1 is 1 over 4. So I can say x squared over 4x plus 3 is equal to 1 over 4. And I apologize, you're going to have to do some squeezing of stuff in order to be able to solve this, okay? So then I'm going to find my LCD, and my LCD is 4 times 4x plus 3. So I'm going to multiply everything by 4 times 4x plus 3. So when I go ahead and I solve this right here, the 4x plus 3 and the 4x plus 3 here cancel, so I end up getting 4x squared equals, and then right here, the 4 and the 4 cancel, so I just end up getting 1 times 4x plus 3, or 4x plus 3. So I'm going to get everything on one side. So I get 4x squared minus 4x minus 3 equals 0. And then I'm just going to try to factor it. Okay? So in order for me to be able to factor this, I need the first term here and the first term here to multiply together to give me 4x squared. So I'll try 2x and 2x. And then the last will multiply together to give me 3. So I'll try 3 and 1. This gives me here 6x. This right here gives me 2x. The 6x is negative, and that will give me the -4x that I want. Okay, so now that I've done that, I can say that each answer right here, I've got x equals 3 over 2, And then here I've got x equals -1/2. But this -1/2 is extraneous because x has to be greater than 0. So this right here is extraneous because it's less than 0. Okay? So I just want to double check to make sure that this is the correct answer right here using Desmos. So if you notice right here, I have the left side of our equation as y equals, and then I have the right side of our equation as y equals as well. And if you look and see where they intersect, it only intersects at 1.5. It does not intersect at our negative value because our domain is restricted. So 1.5 is our only solution for x. Okay? All right, f is an exponential equation, and in order to solve an exponential equation, we're going to want to use inverse operations, so we're going to want to use logarithms to solve this. So what I'm going to do is I'm going to log both sides of my equation, and whatever I do to one side, as long as I do it to the other side, it's totally fine. So it's log of 5 times x minus 4, 5 to the power of x minus 4, sorry, equals log of 3 times 4 to the power of 2x plus 1. Okay, and if you remember, when we have a logarithm and we have multiplication, we can split this up right here into log of 3 plus log of 4 to the power of 2x plus 1. Okay, and then I'm just going to copy the other side down right here. Also, if you remember, whenever we have a logarithm and we have an exponent, we can bring that exponent in front. And that's why we do it, so that way if we have our variable in our exponent, if we bring it out front, now it's a lot easier for us to solve it. So this ends up becoming x minus 4 times log of 5 equals the log of 3 just stays log of 3, and then this becomes 2x plus 1 times the log of 4. Okay, now I just need to distribute through, so I get x log 5 minus 4 log 5 is equal to the log of 3 plus, I'm going to distribute this through again too, 2x log of 4 plus 1 times the log of 4. Okay, now I'm going to get my x's together on one side. So I'm going to get rid of this 2x log 4 right here, and I'm going to subtract it, and now it's going to end up being on the left side. So I end up getting x log 5 right here minus 2x log 4. Okay, and then I'm just going to copy the rest of the equation down as I see it. Minus 4 log 5 equals log 3 plus log 4. Okay, now that I've done that, I want only my logarithms with just x's on this side right here. So I'm going to get rid of this minus 4 log 5. So this is going to say x log 5. Okay, I'm just copying the left side down exactly how I see it. Minus 2 log 4. Okay, get rid of this minus 4 log 5. So I'm going to add it to the other side. So I get log 3 plus log 4, and then here I'm going to have plus 4 log 5. Okay? All right, so now that I've done that, I can go ahead and look and see inside of here, there's an x in common with both of these terms, so I'm going to factor it out. So I get x log 5 minus 2 log 4, and that's going to equal log 3 plus log 4 plus 4 log 5. I haven't changed anything on the right side of my equation. Now, in order to get this x alone, all I have to do is just divide by log 5 minus 2 log 4. So x is going to equal log 3 plus log 4 plus 4 log 5 all over log 5 minus 2 log 4. Okay, so now I'm just going to type that into Desmos and see what I end up getting, because that will give me my answer for what x is right here. Okay, so you can type it into any scientific calculator that you have, and it'll give you the answer that you need. Okay, so let's go ahead and type this in right here. So I'm going to type in a fraction, and I want log of 3, so I'm going to type in log right here of 3. Now remember, we're using log base 10, but you can use log base anything, and you'll still get the same answer as long as you're consistent about what your log base is going to be. Okay, so log base 3 plus log base 4 plus 4 log base 5. So we're going to type right here log base 5, close your bracket, and that's all over log base 5, or sorry, I'm saying this wrong, 4 log of 5, excuse me, and that's all over log of 5, close your bracket, minus 2 log of 4. Okay, so when we finish this all up, we end up getting x is approximately equal to negative 7.7. So here we can say x is about negative 7.7. Now, because it was exponential, our input is allowed to be any x value we want. There are no restrictions, so negative 7.7 is a possible solution. But let's verify this by typing this in to Desmos. We're going to graph out both of these equations right here. Okay, so for the first one, for my first equation, I'm going to say y equals 5 to the power of. Now, don't forget, Desmos is really picky about having your exponents in brackets. And then my other equation is going to be y equals 3 times 4 to the power of, in brackets, 2x plus 1. Okay. And when I look and see where my two graphs are going to intersect, they intersect right at negative 7.671, comma 0. It says 0, but it's not really 0 because we'll never actually touch 0. But it's so close to 0 that it's pretty much for all practical purposes 0. But regardless, all we care about is what the x value is because there's only an x value in this question. And that's our answer to the question, okay? 2 says a sample of radioactive material had a mass of 56.8 grams. So this right here is our initial value, okay? So this is our initial amount. After 5 years, the material decayed to 20.5 years. So this is our T, and this right here is our actual amount. So determine the half-life of the substance. So just a reminder, if you have a radioactive material, if we want to find the half-life is telling us that after a certain time period, the amount of substance in, the amount of mass in the substance decays by half. Okay, so that means it's half of what it was before. So if it was originally 100 grams and the half-life is 20 years, that means that after 20 years, you'll find 50 grams. After 40 years, you'll find 25 grams of the substance, okay? So for starters, we know that if we have a half-life, we will have that the amount of material left is equal to the initial amount times 1/2 to the power of t over whatever your half-life is. Okay, so if it's 20 years, it would be t over 20. If it was 7.8 years, it would be t over 7.8. Now, I'm going to plug in the information that I know. So I know that the a new amount after 5 years, 20.5, sorry, this should say grams, not years. So we know that after 5 years, the material decayed to 20.5 grams. And we know that the initial amount is 56.8 grams. And a half-life will always be 1/2 because it's half of the substance. We know the time is 5 years. I just don't know what the actual half-life is. Okay, so what I'm going to do next is I need to get rid of this 56.8. So I'm going to divide both sides by 56.8, and I get 1/2 to the power of 5 over h. Now, to isolate this exponent here, I'm going to take the log of both sides. So I'm going to say the log of 20.5 over 56.8 is equal to the log of 1/2 to the power of 5 over h. Well, all I need to do here is bring my exponent out in front right here. So I would say that the log of 20.5 over 56.8 is equal to 5 over h times the log of 1/2. So now I need to get this h out of this denominator, so I'm going to multiply both sides by h. So I get h log of 20.5 over 56.8 is equal to 5 log of 1/2. And then to get the h alone, I'm just going to divide both sides by log of 20.5 over 56.8. And then I'm going to go right into Desmos and I'm going to type in that value right here. So when I type that in, 5 times log of 1/2 over log of 20.5 over 56.8, I get this value right here, which is approximately 3.4 years. So we can say, therefore, the half-life is 3.4 years. Okay, and we are all set to go with this question. All right, one more question right here. Number 3, determine all points of intersection of the two functions f of x equals log base 2 of 2x minus 2 and g of x equals log base 2 or 5 minus log base 2 of x minus 1. So the first thing I want to do is I'm actually going to rewrite this as log base 2 of 2 times x minus 1 because I see there's an x minus 1 in common right here. Okay, and then I'm going to find out what my restrictions are. So my restrictions, everything inside of the brackets here has to be greater than 0. So x minus 1 is greater than 0, which means x is greater than 1, and 2 times x minus 1 is greater than 0. But if I divide the 2 out, it turns into x minus 1 is greater than 0, so x has to be greater than 1. So it's the same restriction. So now, if I want to solve my equation right here to see where they're going to intersect with each other, all I need to do is set my two sides equal to each other. So I'm going to say log base 2 of 2 times x minus 1 is equal to 5 minus log base 2 of x minus 1. Now this is where things get a little bit harder because I've got log base 2 here, log base 2 here, but I don't have log base 2 here. So what I'm going to do is I'm going to write 5 in terms of log base 2. So in other words, 2 to the power of 5 is going to give us this number right here. So 2 to the power of 5 is 32, so this is going to be log base 2 of 32. So I can rewrite this here as log base 2 of 32 minus log base 2 of x minus 1, and then that makes everything so much easier for me when I'm trying to solve this problem right here. Okay? Now let's use our laws of logarithms. If we have a minus sign, that means that it's just log base 2 of 32 over x minus 1. And on the left side here, I've got log base 2 of 2 times x minus 1. Okay? Now, because they have the same log base 2, I can set what's inside of the brackets here equal to each other. So I can say 2 times x minus 1 is equal to 32 over x minus 1. Now I know that my LCD is going to be x minus 1, so I'm going to multiply both sides by x minus 1. So what ends up happening is I end up getting 2 times x minus 1 squared, because when I multiply this side by x minus 1, I've got 2 sets of x minus 1. And then on this side, the x minus 1s will cancel, so I get equals 32. Okay? So then I'm going to divide both sides by 2, so I get x minus 1 squared equals 16, which means that x minus 1 is equal to plus or minus 4. Okay? So if that's the case, that means x equals 1 plus or minus 4. So that gives me two answers. Either x is 1 plus 4 or x is 5, or x is 1 minus 4 or x is negative 3. But if you remember, we have a restriction here that says x is greater than 1. So this solution does not work. So x has to be 5. but it said the point of intersection. So to find the point of intersection, I either have to find f of 5 or I have to find g of 5. Doesn't matter which one I do because they'll both give me the same answer if I solve this correctly. So I'm going to say f of 5 is equal to log base 2 of 2 times 5 minus 1 because I'm going to replace this x with a 5. So this is going to be equal to log base 2 of 2 times 4, or log base 2 of 8. And log base 2 of 8 is 3 because 2 to the power of 3 is 8. So this is what f of 5 is. So therefore, my point of intersection has to be 5, 3. Okay, let's just verify this on Desmos. So if I were to graph out both of these functions right here, so my first one that I'm going to type in right here is going to say y equals log base 2 of 2x minus 2. And then my second one is going to say y equals functions log base 2 again. Sorry, we'll put 5 in first. 5 minus log base 2 again of x minus 1. And then I'm just going to see where their point of intersection is. And their point of intersection is at 5, 3. And there's no negative 3 point of intersection because that's restricted for both of those. And that's my final answer. And that's all we need to do for this lesson. I know it was a long video, but make sure that you understand everything for this because this is really the heart of the whole entire unit. All right, I'll talk to you later. Bye.